So this is maybe ISI mock, just ISI mock 5 or 6 anyways in this quarter, doesn't matter. So we're just doing problem 1. So it's about function. So we have a function f r to r. Okay. Given any point p in the domain, there is an open interval containing p such that the image of this open interval is again an open interval. Okay. So given p, there exists, we can just say maybe, doesn't really matter, but yeah, let's say there exists a comma b containing p such that the image of this entire interval, so that's understood what that means, is open. Not just open, is an open interval. Yeah. Then the question is, so let's try to just solve this part. Is f surjective? This is first part of the question. This is easy, I think, easier. Has anybody done this? Was anybody able to do it? Among the papers I saw, I think it was not there. I don't remember. Does it imply that f is surjective? Okay, okay. Mm-hmm. Okay. But how? So if there is rational numbers, okay, okay. That is okay, okay. That is not very interesting in this case. So you're saying that if a Q is not in the range, then what do you mean? You take an open neighborhood. But that may be far off. Yeah, okay. So let's say this Q1, and let's say P1 maps to Q1, okay. So you mean you want to take 2 points or 1 point? Okay, okay. Okay. Meaning like this. Okay. Mm-hmm. Yes. Yes, they are the bordering points of some open interval, right? I mean, yeah, you can just take you mean in the range, in the codomain, right? Yes. So then, because that is certainly, you mean just take this Q2 to Q1. Mm-hmm. Mm-hmm. Why? No, no, no. Why? No, no, no. So there is some interval. That is the catch here. There is some interval around AB, right? Yeah. So this is not going in the right direction. So I'm kind of erasing this. Has anybody else done it? I mean, I know the answer. That's why I'm saying it's not going in the right direction. For this particular question, I know the answer. This part, so I'm saying it. Has anybody else done it? So fine. Let's forget about doing it and so on. Let's. What does this condition mean? I mean, what does it condition? What does this condition mean? Has anyone encountered this condition? For some point. So the domain is R. So for every point in R, it has to be defined. Uh, hmm, uh-huh. Right. Yes. So then, mm-hmm, uh-huh. Yeah, but then that does not form a counter example because it doesn't match the criteria. Right. I mean, this is a criteria, right? It has to be this. It has to have the domain to be R, but that your function is not meeting that criteria. But you are quite, I would say you are quite close in that sense. See, this kind of condition, so if you, even if you don't know, so I have discussed this with some people about continuous functions, but let me not say that now. The easiest thing to do is that, look, this is a very good condition. So first thing is that this is a good type of condition, right? Open intervals are a fundamental thing, and if open intervals are going to open intervals, then that's a good thing, right? So you would expect that all good functions have this property. Okay, you would expect that good functions have this property. Let me also mention this thing, which I have not discussed with all of you, but I think some of you were there. I think Chandan was there, Rasubro, I don't remember. Raghav was there, I guess, also. This thing I had discussed, that if f, so not just if, f from R to R is continuous, if and only if the inverse image of every open interval, any open interval you take, okay, is an open set, which basically means it's a union of open intervals. It is not difficult to prove. You can use the definition of continuity and you can prove. Let me not go into the details and so on now, otherwise we'll not finish and go anywhere. But this is a very, this is the right definition of continuity. That for basically it is saying that if you have this neighborhood here, then the inverse image is also a union of neighborhoods. Okay. So basically, if you take one point in the inverse, one of the inverse, so if you pick a point P here, or rather I should just say maybe Q, and you take one of its inverse images P, then you see, right, around AB there is this Q. So around P, you can pick the neighborhood in which P belongs, and so its image will be in AB, which is what continuity means, right? Small change in the domain will create that required small change, that is AB change in the range around Q. So it's kind of, it's not very counterintuitive that this is correct, but you still prove it. Okay. Now, well, what's the point of saying this, right? Now you imagine if F is a one-to-one function, just for a moment, right? Or any good function, right? If F is a good function, then it will not be union. It will just like, if it's like an injective, a good function, increasing function, then it will be like this, right? Inverse image of open set will be open. And then it's kind of like image of open will be open. Okay. But you actually don't need, I mean, if you just take any good function, just draw any function, this has the property. Yeah, I'm a little surprised that nobody like saw this, right? Just draw this, just any function, any graph, forget about subjectivity. Open, where will it go? So forget about open. You all know IVT, right? This closed, where does it go? It goes to this closed interval, right? What does that mean? It means that if you take this open, then this will go to this open. It's self-evident, right? So you take any function like log x, e to the power x, open will go to open. Like it's not even that there exists some and so on. Like any open interval will go to an open interval. It is basically like an extended version of IVT for good functions. Okay. Now what should the answer be? Not surjective, because there are so many good functions which are not surjective, right? You can just, so now the answer is clearly no. So now anyone can just give an example. You can just take, I think, tan inverse x, right? Tan inverse x, I think might work because I don't remember. It's somewhat like this, I think. Yeah, it is from pi by 2 to not surjective, but open goes to open. Yeah, right, not subjective. That's right. Tan inverse, you can take anything with an asymptote and so on. Okay. Basically, the understanding of this condition is a key. What does this condition mean? That is what, yeah. I was when I was discussing this open properties long time back. That time, basically, I had made this question. So yeah, I didn't discuss this with Adish. So maybe, but yeah, still, anyways, it's good. Now we have discussed it. No. I would just say that it is a property that, yeah, from the perspective of solving it. But how would you know that you have to come up with a trigonometric? Its point is that this property is what you should expect from a good function. You draw any graph with this property is there actually, always. Let's come to that. Yeah. So since we have discussed this, but yeah, for homework, please try this. And you just ask me if you cannot prove this or get stuck. Okay. All of you, please try this because you don't know. This is a good property and it can be useful. Yeah. And just give me one more minute. If I have some other related question, I'll just write it right now, which is no. So I don't have. Or maybe I can just put this more question. If f is continuous also, then show F is monic. This is just an extra question, okay? You can try this later. Yeah, now let's come to the, now let me write the second question. Is F, so let me just think for a minute also, because then you guys also think, because now you have some new picture. So just let's give ourselves a couple of minutes. Okay, so what do you guys think? Summation. Okay. Okay, okay, yeah. So, oh no, no, no. Monic here means, is it? Oh, so it's wrong. Very sorry. What does monic mean? Monotone. Yes, I'm very sorry. And I must just write it. Obviously, in my mind, I have monotonic, but I'm using monic since so long. Sorry. Obviously, there is. So, what did you guys think in the test? Because it's not a polynomial, right? So, how does it make sense to say? Yes, yes, mononomial. Yeah, yeah. That's what it's hard to. I mean, yeah, one can think, but it's monotonic. The question is it monotonic? So remember, it's not given that it is continuous. So will it be continuous? I don't think it should be continuous, but it might be because of the interval, because the range is an interval. monotonic condition. Yes, it need not. So yeah, it need not be continuous. That is right. But that's a rather difficult question. We're not asking that, I think. Yeah, it need not be continuous, but that is difficult to prove, I suppose. Yeah, but is it going to be monotonic? Can we just say that? Is it monotonic or not? So it's just the function, remember, right? Nothing is said about about continuity. So why can't we take something like this? Is this correct with everyone? Because it seems like we can, for any point, if I take a small interval, then the image is obviously open, but it is certainly not monotonic. Double the interval meaning? This is okay, right? If I make like this, then it's wrong. Then the image of every open interval kind of will not be open. Like, okay, so let me not go there first. Let's think about this. Yeah, that will not work. Yeah. Anyone saying something else? Anyone? But let me not go into sin x, otherwise I'll be giving away this answer to this. I mean, proof of this more or less. So let me stick to this and just you can see that this works. Like not, it's not monotonic. Or am I wrong? Okay. Yeah, maybe I think I'm wrong. So let me see. Yeah, what happens? So see, let me just do some labelings because I think something is wrong. Yes, sin x will not work. That's what I was saying. But this, yeah, because sin x, this property is not satisfied. But even this is not correct, I suppose, because because if you take the point one, then any neighborhood you take, you see the image is not open, right? I mean, the image is not an open interval. Neither is it open. Neither is it open. Oh, the image. Where to where? Yes, but then at the point where the maximum is attained, there is a problem. You see, at the point one, for example, where the maximum is attained, this is a problematic point. Because you take any neighborhood, you don't get an open interval, right? You will kind of get, you can see, you'll get a strange thing. The range. So the range will be like this, and this you can say is open, and then the range is also this part, right? So then what is it? So if this is let's say 2, right? So then it is like 2 and some t, right? So t, sorry. So it's like t to 2. Already there is a problem, right? Union something, union 0 to some t1, right? I'm just saying marking the range. So it certainly does not work. 0 is included. So let us just think. Maybe this is true. I don't know how to prove it. Yeah, that's what happens. I just forget things. 1 minute, let me think. should have just seen the questions a little earlier. Yeah, let me just see. 1 minute. I think it is true. Mm-mm-mm. 1 second. 1 second. So let me just see. So if it is not monotonic, we didn't try that, right? If it is not monotonic, if f is not monotonic, then what happens? Can anybody say? Then basically the situation will be like this. Let's just try this for last time, then we'll go to the next one. Situation will be like this, right? Then if the situation is like this, then the image. Yeah, but you can't say that it has a local max. Maybe this is a very hard question. Maybe I have to put the continuity condition, because then it is monotonic. Maybe that's what I was thinking. I just missed the continuity word in the question. Let's just see. So it's not monotonic means it is like this, right? It increases at some point, but then it decreases when you go forward. And then, so you can see one thing, okay, that then in that case, the image of this open interval, you don't know what it will be. Yeah, because there may be some others and you don't know, you may not have a local maxima. Yeah. So then let us do the next one, because I think I may have missed the continuity condition. Okay. So you guys try to use continuity and show that it is monotonic, because in the earlier question we had continuity and we showed it is not surjective. We kind of had a continuous function, right? So in this one, you can just check this, try to prove this. Okay. I will just try this problem again. This may be hard because it's a general function. Or maybe I just missed the continuity word, I think. Just making it so. Maybe it's a mistake. Let's go to problem number 2. Problem number 2, I suppose, is easy, right? That is not my problem. That is, I took it from somewhere, I think. Right? 1 plus a. Has anybody done this? I think this I saw people had done it, I think. But I don't know. Let's see. So you want to find the A, find A such that, yeah, at least one real solution, such that there exists at least one real solution. So, I mean, what is the range of x square by 1 plus x square? Yeah, right? 0 to 1. So yeah, so let's not discuss this one. This one is very easy, I suppose. So basically, this question is asking, I'm just setting the reduction. And you guys, if someone can still not do it, then you can ask next time. But you see, this is the thing. You basically want to find the values of A for which there is a solution of this equation between 0 to 1, right? So find A such that yes, root. There's a root, but you have to solve that there is a root in 0 to 1. Okay, but that's easy. I mean, it should be positive, negative. You can just take some cases, right? It's not very difficult because, yeah, you can do it. Okay, this is a simple, like, it's almost like a GE question. So just try it. This is simple. Next one, I like this because kind of I made it up, I think. Yeah, let's see if that's the right question. So f is a three variable, is it? Something like that. Yeah. So f of x1, x2, x3 is a three variable polynomial with integer coefficients. Okay, polynomial. And so this is written like it is in this z with this algebra x1, x2, x3 being used. Okay. But the very interesting thing is that pi a comma 1 comma 2, this is a very strange thing, pi is coming up, is makes it 0. Okay, show that f has infinitely many roots. Show that f vanishes at infinitely many points. So by infinitely many points, I mean you can take your points to be in complex numbers also. Complex, complex, complex. You can take. That is uh, also fine. Or yeah, just let's think, then we can understand. Mm-hmm. No, 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 that does not work. Yeah, so yeah, yeah, 1 minute, yeah. So see, roots don't correspond to factors in more than one variable. Okay, so I will just say this because this is a very crucial point. Maybe roots does not imply factors. Okay, so when you're in one variable polynomial and let's say 2 is a root, then we know that x minus 2 is a factor because there is a division algorithm, because there is a division that you can do. Okay, so this happens in one variable polynomial, but it doesn't happen, let's say, when you go to two variable polynomials. Okay, and it is very easy to make examples because, and you can just think, right? Because usually, like if you take something like y square minus x, there are infinitely many roots of this t comma t square, but all of them are not factors. But how can we have infinitely many factors? So roots don't correspond to factors. Okay, so that's the problem. Actually, the roots are not so easily visible in multivariable polynomials. Okay, so no, there is, yeah, it is special. Something is special about the pi. Okay, so I let's come to the parameterization thing, then we can see. Yes. So yeah, Atish, you were saying something about parameterization. Mm-hmm. Mm-hmm. Right. 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 So what are you going to parameterize? You're going to parameterize the roots. Yeah. Yes. But then you won't know what U, V, and W are if you're going to say that, right? See, the problem is that this is a very general equation. So you don't know, you won't know a parameterization. That is the problem. If you're trying to parameterize the roots, because there is no pattern in the roots that you can really catch, right? In fact, there should not be a pattern. Yes, I mean, some, yeah, like in, there are parameterizations like t comma t square and so on and so on. But in a general three variable, what can you say? That is the problem. So here is a hint. Maybe I should have mentioned this in the test, but I assume that you guys would use this. This is saying that if you have an integer polynomial in one variable, so basically in the end we are going to use one variable thing only. There's nothing free variable about this in some, we'll see. But if you have a one variable polynomial px, and if px has integer coefficients, okay, then p of pi is not zero, never zero. Pi is never the root of a one variable integer polynomial. This is like a general knowledge kind of thing. We are not asking for a proof of this. This is like the definition of pi in algebraic sense. Yes, yeah, it's called transcendental. Yeah. It transcends the capture of polynomials in some sense. Right? Like rationals are like roots of linear polynomials, right? Then there are square roots which are which can be captured by quadratic polynomials, right? Then any uh, any irrational which you can see can be kind of will have several roots and they can be captured by a sufficiently large degree of polynomial, and that's the degree of irrationality. But pi, the degree of irrationality of pi is infinite. It transcends any degree. So it is extremely irrational. It's transcendental. So we can try to use this. So both are equally irrational up to the gradation of, up to this kind of gradation, right? Because both belong to the same thing that they cannot be captured by polynomials. So in that sense, both are equally irrational. But now if you want to say which one is more, then you have to give a finer sense of gradation, which I don't know where that exists. Okay? Like which is bigger, infinity or naturals? Now both, sorry, R or N, which has more size? Now both are infinite. So in that sense of gradation, there is no comparison. Both are equally big. But then if you further put a gradation like bijection, is there a bijection between sets and we call them same size and so on, then R is bigger because there is an injective function from naturals to reals, but there is no injective functions from reals to naturals, right? So that means R is bigger. So yeah, but I don't think there is any gradation here, at least from what I know. No, we have. Just like this, you think you said about, you said no, this tan inverse thing. Use that, you put X, you say, I'm just answering from your own thing, right? I mean, just, yeah. So in that you put one, just saying it for others also, tan in the expansion of tan inverse, you put one, X equal to one, you'll see you'll get a expansion for pi by 4 for pi. So yeah, so both are equally bad in that sense. But I feel that pi is worse because E has a very interesting limit, very easy limit, right? 1 plus 1 by n to the power n. Pi doesn't seem to have such a, but anyways, yeah, it maybe, yeah, it does have actually. Anyways, leave it. Let's think about it. So try to bring it to one variable case. We did this right in some, when we were doing some three variable polynomials and things like that. And I made this question last year. Yes, yes. Uh-huh. So how will you use? So now that you cannot factorize, how would you, yeah. So maybe you can think of an alternative without factorizing. Uh-huh. Right. Right. Yeah, that's it. So let me not say anything more from here. Okay. Yeah, it is just that simple. Yeah. Yes, with integer coefficients. No, no, no. So you see, transcendental is important, right? Because see this, because now we have G is an integer polynomial and integer coefficient. No, it can have irrational roots. Why? It can have irrational roots, right? I mean, obviously. Yeah, right. So yeah, it will not work. Okay, that's why you were saying no, it will not work for any. Yeah. So G of pi is equal to 0. It implies that G is equal to 0. Like G is identically 0, which means that it will have infinitely many roots. And in fact, infinitely many points uh, in Z3, meaning integer roots, right? So in fact, Z, Z comma 1 comma 2, all of this will be roots. So it's a stronger thing which you can prove, right? We don't need to go to complex. We can just say that even in integers, there are infinitely many integer triplets. Okay. Actually, this is a much more special case because in fact, it turns out that any three variable polynomial always has infinitely many roots. Okay. In fact, if you take two three variable polynomials, their set of common roots will still be infinite. But that's a much more difficult thing to prove. Yeah. So we will not see that. But this was rather simple. Okay. Any questions in this? Yes, yeah. That is, yes, yeah. In fact, that is the way it goes. That is the way it goes. That is right. Yes. No, so you can kind of break it down to one variable and show that there is a root because every one variable polynomial has a root in complex. Yeah, so you have to kind of fundamental theorem of algebra. So you have to use that and somehow do it. It's not very difficult. But there are very interesting results that if you take any three variable polynomial, then the set of and you take a plane, then the set of roots that lie on that plane are going to be finite. Or yeah, they're very interesting results. But we will see it. Next problem is okay. Let's move to the next problem. So let's see what is the next problem. No, no, it's number 4. This show that this is an integer. That is very easy. Okay, let's see. Yeah, so that's let me at least. I don't even remember know the question. Let me see. Then this is 14 factorial, right? It's only 90. Then why have I put double brackets? Yeah. No. Okay, I think it will be 90 factorial. Yeah. Now it's this is 900. This is 90 factorial. Otherwise, it's very simple. Yeah. This is an integer. You guys should have asked me because I mean, obviously, first of all, I should not have made this mistake. But yeah. Anyways, Yeah. Mm. 1 minute. Yeah, okay, you can do that. But yeah, you can, but I'm not doing that because it will destroy the symmetry and so on. But maybe that you can do that. Let me also think. Mm. Which formula? Okay, yeah. So certainly you can use that to do this problem, right? You can, because see, these numbers have very simple prime factors. So you can always use the, calculate the highest prime in each of them, and you can see it's positive overall for every prime, right? You can certainly do that. But the question is there a good way to do this problem? So this can be done by pure calculation, okay? So just take the valuation of every prime, right? So for each prime which is relevant here, check its final multiplicity and show that. Right. So then you can check for the small numbers also. Right. Hmm. And which is very easy to check. So it can certainly be done like that. But I made this question, I think, with some combinatorial thing in mind. So basically, the idea is that I suppose, which I had in mind, is that is there a combinatorial problem whose solution is this? Okay. So is this, let's call this T, is T the solution of a combinatorial problem? Because that will be a better way to prove it, and also when this is like replaced by general expressions like a factorial b factorial, then also it can be a good thing. But now I am a little confused because there is a 14 and Yeah, that was my basically my goal. Can you break it up? Now that I see a little bit, I can understand that maybe if I break it like this, then that can be a hint. No, no, certainly not. I didn't intend to do it computationally. Certainly not. So if you just focus on this, maybe you can get some ideas. So I'm just breaking it up like this. Now, this part is, you can understand why I've written this part will take care of its own. This part, I want you guys to show that there is a combinatorial problem whose solution is this. I mean, there are many difficult questions like this. I will not take the 6, let's say. Actually, yes, maybe you can take it. Yes, yeah. But even if you, let's say, so from this, just for the sake of it, yeah, you can take the 6 and actually that will also be an integer. So actually it will not be a problem. Yes, yes, that's right. But my claim is that this is also an integer. Oh, no, 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 no. No, no, no. I get that, right. But my question is that even if you forget the 14, this is also an integer. And so let's forget about the 14, and this is also an integer. And the hint kind of is to break it up like this. Now you have to think. Now it is a bit more than multinomial coefficients. Multinomial coefficients, I understand, but this is a bit more than that. Right. Yeah, but then there is a connection, but then there are more identifications because this 10 is appearing here and this 6 is appearing here. So these 6 kind also have some sort of further similarity in them. So you again having that 6 factorial. So think, okay, this is just the hint. It's, you can think about this. This is a very cool way to prove that such things are integers. And there are other problems like this, which for which, combinatorics seems like the only way to prove it. Okay? Very strangely. Think of a combinatorics problem. That's there's a real merit in doing it like this, right? Because then you have a different way, really. Yeah, so let's do let's do one more question. Okay, I shouldn't be saying this, I'm a little sleepy today. Okay. So, but let's try this last question. Okay, let's 6, 7, 8. I will certainly do it tomorrow. Okay, in the class. I mean, I will do other stuff, but we'll do this in the end. But let's do 5. Let's try 5. Oh, but I couldn't do 5. I was just trying it while eating. Huh? No, but you can define it. You can. Or then okay, then since 2 people have done it, maybe then it's fine. Okay, but then can you quickly give us a hint? Can you give a hint? Do it backwards. Okay. You mean, so you mean from an you go to, then you do an plus 1, an minus. Okay, do it backwards. So can you just tell us one step? Plus 1. Yes, that's what I was thinking, but then I don't know. Yeah, yeah, let's see. Then in this only. Okay. So you write x raised to n t. Oh. Hmm. Hmm. Okay. Hmm. An plus 1 is. Okay, okay. So this, no, so can you just say more? Oh, sorry. An plus 1. So this will just be an, and this will be like this. Okay, like this. Is this right? Oh. Ah, now I understand. You can further take out and so on. Okay, okay. Ah, okay, okay, okay. Now I understand. Okay. Yeah, so I was not getting this. I was doing something else. I was trying some other things. Okay, okay. Mm. Yeah, but when you write an like this, then you get x raised to n minus 1. Same thing. Ha ha. Yeah, that's what I was. Yeah, yeah, yeah. Okay. Then, but then you can again pull it out. Okay, okay. So does everybody get it? Those who, if someone could not do it, like me, I couldn't do it. Okay. If not, then say, because you should know how to do it now. Okay, then it's fine. So then let's try the seventh one. That is the demand. Seventh one. Eighth one also you have done. Okay, okay. Okay, okay. Let's do it next time. Okay, sixth one. Yeah. Oh, then it's good. Yeah. Induction also. Okay. Yeah, but that's not difficult. Yeah. Let's do this one. Number 7. So n has, so this is a problem with, it's my, I had made it, but now I don't know how to do it. So you can see. Okay. So then it's also good. N has at most, so let's say n has at most 5 ones for a minute. Okay. So we are looking at those numbers which have at most 5 ones, not more than 5 ones in their expansion. Yeah, like if uh, okay, no, then it will be trivial. Yeah. So anyone has done this? Okay, no. So at most 5 1 means that it means that it's in the 1 by n. So example, we cannot take a number like this. This is not allowed because this has 6 ones. Yes. So those natural numbers which have more than 5 ones, those we are not going to take. One by those numbers 1 by n we are not going to take. Okay. Other natural numbers we are going to take. So this will not be in our expansion. This n we are not going to take. Is it any clear now? Yeah, like this is okay because it has 5 ones. Okay. So we want to show that this summation is finite. So I don't know, some of you may know, there was this ISI question where they were saying those numbers which has no zeros, right? I think it's a famous problem in tomato, no zeros. Yeah, it has a bound. This is finite and it has a bound, 1 by something, 90 or something, whatever, I don't know, whatever, something like that. Yeah. So it is now, so I was taking this question and obviously ones you can replace by zero. See, that is not a problem, right? If you can do it with zero, you can do it with ones. But then I thought, okay, no ones and can make it 1 1 2 1 5 ones, finite number of ones. It is actually still finite. That's the basis on which I didn't make it. I just generalized it. Okay. Now, how do you prove this? Let's think. So you have to use a similar idea of comparing kind of, yeah, I think powers of 10, because now let's do it for zeros only. So yeah, so basically you can go all the way from 0 to no, 5 zeros. So you can go to 10. Yes, in the end that's what we're going to do. You have to put some upper bound. That's the way to show. What will be the upper bound? How do you put it? No, but it will be summation of many things. It's an infinite summation, right? Yes, Raghav, you saying so? Yes, yeah. Basically, we have to put an upper bound in the end. Yeah, we have to put some upper bound. So maybe we can. I don't know, because 5 zeros. Wait. One minute. Yeah, it's not very difficult, right? You just take you take numbers from 1 to, you take all the way till 10 to the power 5 minus 1, right? This you can say. No, don't take 10 to the power 5 because that, okay, I thought, yeah, that's allowed. I'm sorry. You take these numbers and so these are all fine, right? And then you have this huge interval. No. Yeah. Then you get 10 to the power 5 plus 1. No, this is also fine. Hmm. No, so you have to go to 10 to the power 6 minus 1. Yeah, 6 minus 1. Something like that you have to do. So till here it is fine. Then you don't take 10 to the power 6. Then what happens? Then what is the next number which has 6? No, but it will have a decent bound because you'll see the bounds are still there. So when is the next time you get more than 5 zeros? That's a very straightforward thing, right? You get it when you get no, 2 times 10 to the power 6, right? 2 times 10 to the power 6, and then you have 3 times 10 to the power 6, right? And so in between, 1 minute. Yeah. So it's not difficult. So you see, from basically you have to say that between 10 to the power 6 and 10 to the power 7, how many? So this is a very simple counting problem, right? So between 1 and 10 to the power 6 minus 1, there are number of way to arrange more than 5 zeros, and that is it. And then those which don't have 5 zeros, don't have more than 5 zeros, that's the thing you're going to take, right? So for example, the contribution of this in the contribution in the summation is going to be less than 10 to the power 6 minus 1. I mean, it's going to be much less than that, but this we can say, right? Because this is less 1 by 2 is less than 1 by 3 is less than 1 by 4 is less than 1, like that. You get this, and then you have to just see that between these two numbers, between 10 to the power 6 and 10 to the power 7, if there are x numbers, and this is not difficult to calculate, x numbers with at most 5 zeros, you can calculate this. Then the contribution will be less than x times 10 to the power 6. Okay. And then similarly, between 10 to the power 7 and 10 to the power 8, you have whatever you can do, x6, x7, and you will get some sort of an arithmetic geometric progression and so on, which will have finite sum. You don't have to find the sum, you can just say it's finite. You can also find it. This is the idea. It's just a simple counting problem with this kind of bounding. Is the idea clear? Now you can try to finish it. If the idea is not clear, you should ask. And if you're still not comfortable, try this with 2 zeros. You can see you can do it similar way. Okay. So no zeros are fine, but we are also saying, okay, you can take 1 zeros, 2 zeros, 3 zeros, 4 zeros, still 5 zeros. Then also it is finite. There are other better ways to do the distribution of numbers with no zeros and 1 zeros, they are same and so on, but this is cool. So if the idea is okay. Okay, so I'm not going to discuss any of the other questions today. Not feeling very bright now. So, but yeah, but this one, just just maybe I'll keep the meeting open. Okay, so in 2-3 minutes you can just ask questions. Okay, if anyone has, and if you don't have, then you can leave, and then I will know that no one has questions also. Take your time, go over the things we have discussed today, and you can ask. Mm-hmm. You can use, usually you use integrals. Integrals are one way because integral by definition is the summation of an infinite, non-trivial infinite series. Yeah, that's why. Integral actually also proves the convergence finding, Yeah, integral is one thing that comes to mind. Obviously, there are other things which may work, like some sort of manipulation. You can use some sort of recurrence. You can you can identify it as some Taylor series. You can use some telescoping. I don't know. There are so many ways, right? So there is no end to those things, and I don't really know much after that. Okay, then it's good. Maybe we can see that next time. Last question. I don't know. This was I've taken from some Olympiad. I don't know how to do it. I have to think. Okay, you're getting an integral. Okay, so then that should work if you're getting that. If it's working. Okay, so then no one has questions. So then yeah, and then turn it off. Okay. Yeah. Okay then. Thank you. Next class I will take tomorrow. I'll take a calculus class tomorrow. We will. What were we doing last time? Yeah, last time we did something else, right? But no, but next time we should do. Yeah, we'll do integrals. Yes, yes, yes. Yeah, but that, yeah. So what tomorrow we will do. But what did we do in the last calculus class? Yeah, we were making the function, right? Which is, and also that was simple. But after that, we were doing the non-differentiable thing, right? Yeah, we did. Yeah, so we basically had this function which is infinitely differentiable, but it is suddenly zero outside an interval, and we were making this example. Yes, matching class I took last week, which I think you missed. Okay. So I forgot to upload it. I will upload it just now, maybe morning, maybe I'll do. I think I'll upload it now because now I'm not fit to do anything else. I'll do it. Yeah. Yeah. Counting class, I think counting we have done enough. So I'm not doing counting right now. Okay. Better to do some polynomials and so on. Right. Uh yeah, I think I have a few more mock tests which you can write. That is better than assignments, I think. Because problems anyways I give in the class. Even today I got some 2 3 problems you can try, but mock test is better. Okay. Hmm? Geometry, no, that is not, see, that is not for you, but you can obviously try the problems. I think there are some problems are interesting which you can. Is that the geometry you're asking or what? Yes, it is a proper course, but it is for juniors. So obviously you can see there are some interesting problems. Like if you just scroll the video to the end, you'll see some problems I give. You can try them because they are good actually. Okay. But the whole class is very slow. Like it's extremely slow because it's like there are some kids, class 7, 8, and so on. Okay. So yeah. Okay. Thank you. Bye. तुम इतना जो मुस्कुरा रहे हो. Grade is AB. AB means 9. Man, sure. खेल किया था पहले. Yeah. AB means 9, right? Because B is, yes, unsubscribe. Because I don't want to open them. आंखों में नमी, हंसी लबों पर. ओ बाबा. Yes.